Hello, today I am going to talk to you about the James Webb Space Telescope and the problems it poses for scientists, with perhaps the start of the beginning of a solution. But first, I would like to thank my 8 subscribers for their perseverance. I need to try to make videos more often in the future.
I promise nothing.
This telescope is designed to operate in the infrared, and as the light from galaxies moving away from us is shifted towards red, it can capture images of objects much farther away than its predecessor, the Hubble telescope. The problem arises because it has discovered very evolved galaxies and supermassive black holes at a time when they should not have had the time to form. The problem is so significant that some have even considered that the Big Bang never happened. At that point, other problems would arise. Not only the problem of explaining the redshift of galaxies, but also the problem of the evolution of the universe. Because in a universe that has no beginning, one cannot observe evolution. The changes in the chemical composition of galaxies, the heavy element content, which is not the same for distant galaxies and for nearby galaxies, and evolution also in the stages of evolution of galaxies like the quasar stage, which no longer exists today. Most physicists try to reconsider the theory of galaxy formation, but it also poses enormous problems regarding the constants in physics on all levels. What does the theory of relativity teach us? Time does not flow at the same speed for an observer on Earth and for a traveler at high speed. If this traveler observes the universe through the window of their spacecraft, they will notice that all the events in the universe are occurring in fast motion. To give an example, at 86% of the speed of light, the ratio is 2. That is to say, the traveler will see all objects in the universe evolving twice as fast as the observer on Earth. And if he can communicate with an observer on Earth, he will hear him speak twice as fast, while he himself will be perceived in slow motion by the observer on Earth. And it does not depend on a Doppler effect, even if the distance does not change between the observer on Earth and the traveler. For example, if the traveler is in orbit around, in high-speed orbit around the observer, do not confuse the Doppler effect with the relativistic effect. The ratio is the same. The time of the observer on Earth is not the same as the traveler's time. This is well known and has been verified. The principle of equivalence tells us that gravitation produces the same effect as acceleration. An observer in an enclosed space does not differentiate between being in Earth's gravitational field, like we are right now, or accelerating upwards.
As we are in the gravitational field of the Earth, the solar system, the galaxy, the entire universe, however, we are in the same situation as the high-speed traveler,
in which is in constant acceleration, weak but constant. And when we look through the portholes of our Earthship, that is, through our telescopes, we should see all the objects in the universe evolve in fast motion, and expansion is no exception. This is what I had published in a small journal, and the article went completely unnoticed before the discovery of the acceleration of the expansion of the universe. And so It might well be that the acceleration of the expansion of the universe is simply a relativistic effect due to us being in a gravitational field. And that's actually what makes me doubt. It's that if it were that simple, it could have been discovered a long time ago. The consequence of all this is that the unit of time is not constant. It evolves depending on where we are, the era we are in the universe. And we encounter the same problem today with the Space Telescope. If the unit of time evolves, extends, then in the past it was shorter. I will give an example to be
Clear. Let's imagine
a galaxy moving away from us at 100 kilometers per, let's say 105 kilometers per second in, let's say, 25 billion years. Logically, the expansion should slow down. And let's say it moves away from us at 100 kilometers per second. But if the unit of time is twice as long, observers of that era will see the galaxy moving away at 200 kilometers per second during the second of the era, which is twice as long. And the observers of that time will notice that the expansion of the universe is accelerating. And when they measure the age of the universe, they will find 13 plus 25, 38, divided by 2, 19. And will be entitled to wonder. But why is the universe so evolved after only 19 billion years of existence? And it's the same case that happens probably in our time with the problems posed by the James Webb Space Telescope. It is possible that in the first millions of years of the universe, what we consider the first millions of years of the universe, because we measure them with the time unit of our era, actually several billions of years went by. Then the difference fades compared to our time unit. In fact, the difference is probably exponential as we get closer to the Big Bang, that's why it's the first millions of years of the universe that pose big problems with time unit differences. If indeed we find galaxies as evolved 200, 300 million years after the Big Bang, it's because there were not really 200 or 300 million years. There may have been 10 billion years during this period. An observer who was born at the moment of the Big Bang, and could have witnessed the entire evolution of the universe with a watch on their wrist, could find much more than 13.8 billion years today, and that actually poses the problem of question the nature of time. Could time not be a vector of entropy, or whose intensity could vary depending on the level of imbalance of the universe? The notion of imbalance is very important in understanding the universe. I will come back to this in another video. Time could be a bit like a river that flows more or less quickly depending on the slope.
something to ponder. Thank you.